In this video, we're going to look at how we can study our optimization process and in fact track how it's going along the way, because a lot of times, especially in more complicated examples, it becomes important to recognize when things aren't working or when we found an answer that makes no sense. We'd like to be able to get that kind of insight as the program is running. We're going to do that in two different ways. One, using an option for the optimizers themselves in MATLAB using OptimSet. And what that's going to let us do is display the search status every iteration. And we're also going to see a second way to achieve this goal, which is by modifying our objective function so the output is displayed each iteration and maybe in a richer way or more informative way. We'll start with the bare bones version though first, displaying with the optimizer tools. So we're going to use the OptimSet command in here. And of course, if we want to find out how that works, we can look it up in the help menu. And not surprisingly, the OptimSet sets values in this kind of pairwise fashion. And the options are down here. And we've been given a hint in this case. We'd like to display things as we're searching. And we'd like to display things every iteration. That seems like a reasonable place to start. So how does that code work? We go down to where we're actually doing the search. And then just before that, we say, I'd like to create some options using the OptimSet function. And the value we're going to use is display, and I want to display every iteration. Now, it's not enough to make those options. We also have to add them to our search point, or to our search algorithm. So now we would read this as, please search our function for a minimum in an unconstrained way. Here's my function. Here's the starting value. Oh, and by the way, please use these options in addition to the default options. If we run that, we're going to see basically the same output at first glance. But if we scroll up a little bit in our output, we see much more information. Let's make a little room here. We see an iteration count. We see a function count, which is essentially how many times we had to go to our formula. And we also see the f of x values. So if we take a look at our picture, and let's move our point in to say -1, 4, just for the sake of argument for a moment here. Start up -1, 4, and run that again. We're going to see that we started around 180 as the function value. And sure enough, when we look at our values here, at our starting point, we had a function value of 176. And then what we see are the numbers going down and down and down as we are doing our minimization search. You can also see that we got very close to the optimum by here. The last 5 steps were all little searches around the bottom of the valley looking for minute improvements at the end of the search. There's some other ingredients here that are far more technical. First order optimality is essentially something like the gradient estimate, and the closer to 0 it is, the more likely we are to be actually at the bottom of the valley. But these should also be heading towards 0. Step size is technical stuff about how the search is being operated. But the key thing is, especially if this were a lot slower, is we would see this output popping up. And especially if we started seeing the same value over and over and over again, we would start thinking, well, this is not improving much. Maybe I should stop. Maybe I should try something else or choose a new starting point. So this gives you some indication of the progress of the search. From that, we get an idea about how many iterations it takes. We can see that in the answers here. It took 10 iterations, or about 36 function calls. 10 iterations. And that's not bad. That's actually pretty quick. It's certainly faster than we would have done by guessing and checking values, hoping to hone in on this point here. And also we get a pretty high accuracy answer for the location as well. Now there are limitations to that display. It just shows our function values. We might want to see, not necessarily every time, but we might want to see the x vector as we're going. Or for us, it was the vector v that we're talking about, which is our x, y values as we're searching. Our next step is to see if there's an alternative way to do this search, which will display those values as we go. If we do want more detail in the output as we go, what we can do is make our objective function a lot richer. This is the key ingredient for our objective function. You tell us x and y, this function gives the function value back. but we can piggyback on that to do other things with the x and y values at the same time. What we're going to do is create a new function called f1 plot points, which is going to do both. It's going to calculate this function value, and it's also going to plot the location of where we are currently. So here's how that's going to work. We're going to create a new file, f1 plot points, and it should start with the word function, and it's going to return an f value, and it's going to take an x and y in. So it's essentially the same as our function that we started with. In fact, it's so similar, we are going to cut it out of the original and paste it into here. All right, we'll save that as f1 with points, perfect. And if we do this, we should be able to run our algorithm exactly as is, except being careful to take this out. That was the syntax that said this was a function. Now we're going to be coming into this MATLAB formula with an x and a y, and we want to sub them right into this thing here and calculate the value. So we should be able to run almost everything the same. The only thing that changes is this is f1 with points, and f1 with points here to create our contour diagram. And the idea, f1 plot points. The idea is that it shouldn't matter now that we have our new formula, because the MATLAB file, blue dot, red dot, perfect. This MATLAB file just does what we had it doing before in a one-line anonymous function. So we've done nothing new so far except separate this out into a separate MATLAB file. Where's the perk? The perk comes in when we actually can plot the x and y points. So we could plot the x coordinate, the y coordinate as a dot. Let's make it a red dot, maybe a little smaller, maybe 10. And if we do things carefully here, what's going to happen now is when we call our FV function as we're optimizing, we're going to be calling our plot with points function, plot points, and so it's going to plot a point as we go. Now that's a bit awkward because we actually want to plot this over top of the contour diagram for it to make sense. And actually in this case here, there are times where we don't want to plot anything. So I'm going to bring this function back to our main code. We'll want that when we're generating our contour diagram. But when we run our search, we want to use FV, and FV should plot the points over top. So let's see how this works. We're going to search for a minimum of FV. FV is going to call our function with v broken down into x and y. When we get a new x and y coordinate, we're going to calculate the height, but we're also going to plot a red dot. And that's going to work perfectly with the contour diagram being plotted earlier and a hold on so we actually see the red dots as they appear. And the only thing we might want to do here is put a little pause. Let's try a half-second pause, just so we can see things as they're happening. So let's run this, and we're going to discover there's a problem in our W10.1. Right, we took out the function formulation here. So that function still is a function. Oh, then we have an error here, which is I spelled marker size wrong. There we go. Run again, and here we see the process. We started here, and what we're doing is we're searching down into the valley. Every half a second we're getting a new iteration, and we can see that we're gradually diving in towards that minimum, and we know after 10 iterations we're going to stop. So what we get at the end of the day is our starting point and our search pattern down to the bottom there. If we change our start point just to see what else can happen, let's start from, say, maybe 0.5. When we do the search this time, this is our starting point. You can see that we're kind of searching down along a line, and then, oh, this is sort of the best point along that line. We search in again, then we sort of take a turn, and we take another turn, and we're already down in this valley. So we can use our function and the plotting ability in it to trace where we are as we're searching. And again, that can provide us some extra information as we're doing the search. Not so crucial for this particular application because the function is simple, but in any other application where things are complicated, it's incredibly useful to be able to report this kind of information. If we want to, we can also add a quick little title, and that could be using our sprintf. We can create a separate variable value that we can put into a title, and we can say our f value is to 4 decimal places equal to f, and close our brackets there. If we make that kind of change, and we'll just speed up the search a little bit here, only a 0.2 second pause in between plots, we can see the title up here is changing. It's trying a bunch of different values. Not all of them are lower, but in the long run, these values do go down until we reach our local minimum in this valley here. And so that's how we can trace down and use an objective function to find different local minima. Notice that we can see a bit of this linear search idea from here. If we drew a line that was roughly the gradient, it would point uphill. What we're doing, or what the algorithm is doing for us, is tracing back down that path, and then it found a different path here, found a local minima in that direction, turned a bit, went in this direction until it found a local minima. So it's doing this turning and searching process as its underlying search algorithm to find local minima. If we had to compare those two techniques, using the display iter option or expanding our code, this is certainly easy, but I would say often not very informative. It's better than nothing, especially if you have something that's taking a while. If you don't turn this on, you'll just see MATLAB sitting there. You'll have no idea what's happening. However, if you have this display iter on, you'll at least see this kind of output every once in a while, reassuring you that MATLAB is still working and generating new solutions. However, the expanding code in your own MATLAB objective function is far more versatile. You can customize it to whatever you like, put as much detail, as little detail as you need in there, but it obviously takes longer to code. So there's always this trade-off of how much do I want to put in there to understand what's happening versus let's just get this thing running, searching, and pumping out the optima for me. That choice, always, as always, uses the professional judgment of you as the coder as you're working through a problem.